So I want to thank the organizers for giving me the chance to talk, and this is the first chance I've actually had to give a seminar to this group of people. I've been here for the month and I'll be here through December, so now I feel like I'm actually going to contribute something back, hopefully. I'll be talking about a grid that has probably not been sort of widely used, or sort of a two-patch sphere grid that we've developed for modeling transport in the atmosphere, and I'll also be talking about adaptively refined two-patch sphere grid. Okay, and this is joint work with Carsten Burstedt, who's here, and also work with Marcia Berger, Christiane Helzel, Randall Levesque, or people that I've sort of discussed a lot of these ideas with. So I guess I sort of thought I should talk about where I come from and kind of what started this whole project that I'm going to describe. So I come from a background, I know something about finite volume schemes, wave propagation algorithms, on logically Cartesian grids. I know something about solving PDEs on spheres. I got into this business by looking at diffusion equations on, solving reaction diffusion equations or something on spheres. I know something about block structured adaptive mesh refinement, and Phil Colella did, and sort of set the stage for sort of everything that I know about that world. And then I've had experience with lots of these software packages for doing the above. ClawPack, developed by Randy Levesque, AMR Claw, Chombo Claw, BoxLib, lots of these libraries. And then there's many more. I actually maintain a website of all these software, of several software packages for doing kind of adaptive block structured AMR. And then I add to this sort of a belief that, if you're going to be in the business of designing numerical schemes in the 21st century, probably you should start with some idea as how you're going to adapt your scheme and how you're going to scale, and how will it scale to large numbers of cores. I have Phil to thank for planting this ridiculous idea in my head. Some appreciate. I have actually. I was trying to find a stronger word than appreciation. The essential sort of need for people, to have domain expertise in some area of application, a desire to be more than just a user of other people's codes. I actually kind of always had in the back of my mind, I wish I had my own code that, no matter how good other people's codes are, you would always do it differently. And so I somehow was very much, had that bug. And also a full awareness of the ridiculousness of trying to do the above by myself, at least while on a tenure track position in a math department. So, I didn't get off the ground until several sort of fortuitous things happened in the last year and a half or so. I went to a workshop at NCAR, organized by Peter Lauritsen, on tracer transport on the sphere, and that was really a nice entry point for someone who's kind of interested in this area, because you get to meet a lot of the people, you get to look at the problems they worry about, and the benchmark examples are easy enough for someone to start with without a lot of sort of physics in it. A meeting with some USGS researchers at the Cascade Volcanic Observatory, interested in using adaptivity to improve their forecasting of volcanic ash cloud transport. A hands-on workshop where we actually did coding on high-performance computing held at KAUST back in March of this year, where I got to meet a number of people involved in kind of high-performance computing issues, and then finally this opportunity to come here for the semester on this program on multi-scale numerics for the ocean and atmosphere. So I put all that together, and what has come out of it is this code that we're just now getting going. Okay, so I'm going to talk to you about various pieces of this. We call it Forest Claw. It involves pforest, which is a code that Carsten Burstedt developed to manage quad or octree of non-overlapping fixed-size grids, which is perfect for the AMR setting. Wave propagation algorithms that I had some familiarity with, okay, on mapped Cartesian grids. And this sort of application target, the aim is to improve the forecasting capabilities of ASH3D, which is an existing code that this USGS group in Vancouver, Washington have for modeling the transport of volcanic ash. And this particular model is quite well suited to AMR. So I say a few things about wave propagation algorithms. These are finite volume schemes on logically Cartesian grids. First and second order, with or without limiters. There's split and unsplit options. I'm sort of describing the implementation, which is in a code called ClawPack. Okay, the wave algorithms are sort of the more theoretical kind of underpinning for the code, I guess. Second order accuracy is achieved by propagating second order correction waves in normal and transverse directions, and it's a CFL limited explicit time stepping scheme. And so the idea is really simple. You know, I mean, we have some kind of advection going left and right, and we sort of call, I don't know if I know, do I know how to use this pointer? Maybe not. You know, we just sort of call this thing a wave. This jump in values between cell average left and right values, we call a wave. This thing right here, okay? So that's where the wave propagation comes from. And depending on whether you're going left or right, the wave kind of appears here, and I'll show you in a minute. So a basic sort of a first order upwind scheme would look something like this, with these sort of terms here that we write in this kind of funny way with W, which is what we call the wave, and that's the thing that propagates, okay? And how do we get those in a multidimensional system? Well, you've got characteristic speeds and sort of eigenvectors, so you can think of maybe solving a Riemann problem to get this information. And then we have what are called fluctuations, which actually update the cell average based on stuff that's coming in from either the left edge or the right edge, okay? High order is achieved by including, high order, second order, excuse me, is achieved by including sort of correction, linear correction terms, okay, that have this conservative kind of flavor. In 2D, it looks something like what I guess I'm seeing a lot of these kind of semi-Lagrangian type schemes. I mean, they sort of all have that flavor, but here's kind of this normal first order correction, and linear correction is obtained by sort of propagating this thing in this direction. And then what happens is that this little triangular area contributes to a flux at this edge, this little piece contributes to a flux at this edge, and you get an accumulation of fluxes that add to the, that sort of increase the order of accuracy of the scheme, okay? So in fact, these corrections include both linear terms and transverse propagation. In a more kind of notational, this is kind of the whole scheme written out, and all this can be reformulated as a Lax-Wendroff scheme. The types of equations, it's sort of, you know, all the stand, obviously, a conservative law or a conservation equation, quasi-linear form, a transport equation, flux functions that are spatially dependent, and of course things with source terms. The fact that these can all be handled in this sort of uniform setting is sort of nice, so we don't really have to treat something in conservation form any differently than something in, say, quasi-linear form. Okay, so we want to do this on mapped grids. And we do rely on smoothness of the mapping, so we rely on the fact that we've got a nice Cartesian mapping, that sort of a mapping that maps computational space to something smooth. We compute metric terms, but we really only approximate discrete versions of these things. So for example, the sort of what would appear over here as part of the metric tensor are simply just lengths of vectors between kind of the the centers of a say a primal grid and the nodes on some sort of dual grid, okay? And all these quantities can be computed that way. We don't do it this way necessarily, but in fact the area, for example, is simply some way of computing this thing. Okay, so in our case what we do is simply compute the area as, or lengths, or so lengths are approximated by lengths of these vectors, and normals are approximated like this, okay, again, calculate using discrete values here. Areas can be done using sort of the area of a ruled surface that approximates your mapping. And all these things are put into the basic algorithm. They have sort of natural places where they appear in the basic algorithm. So really handling the surface is no different than sort of treating the sort of the unmapped case. The grid we want to work on is this, what we're calling kind of a two-patch grid, I guess. We've yet to kind of have a name for it, But we described this in a SIAM review paper several years ago. And the idea is that you start with a logically Cartesian grid and you just sort of fold it underneath itself until you get a sphere grid, okay? It's not orthogonal particularly. It has seams and it has discontinuities, so you can't get rid of the pole problem. You can't make it go away, but you can distribute it more evenly, okay? So in our case, the grid is mapping is discontinuous around the edges and across these diagonals, all right? So I guess some people have called it a pillow grid, which I don't know. That is actually the most descriptive term I've heard. So I haven't decided whether I want to call it that, though, because it doesn't seem very serious. But anyway. So then there's P-forest. So we've got all this kind of wave propagation code back there, but we want to use it in an AMR setting. And that's, of course, already been done. Chombo Claw, I think I wrote with Phil 10 years ago or something, or using Chombo. AMR Claw has been around for a long time, but I sort of wanted to do my own thing. So fortunately, I met Karsten Burstedt at this meeting in Kaust, and we got to working together, and are now, I'm now using his code to do the AMR part of all this. It's a parallel multi-block code for managing a forest of adaptive quad or oct trees, highly scalable on realistic applications of interest to geophysicists, and here's just an idea of the scaling. So you probably should really talk to Karsten. He's here to get details of this graph, but they've run on up to 220,000 cores, 5 to the 10 to the, what is that, half a trillion points? Some 5 times 10 to the 11th elements. Okay, I think this was maybe a DG calculation. And this slide shows basically some kind of weak scaling. It's a tree-based code, so everything is laid out. Cells are nicely laid out, and so you basically can get scalability while preserving data locality, which is essential for sort of an AMR code. So neighbors are more or less on the same processor, and here sort of, it's a little hard to see the colors, but everybody here would be on one processor, everybody here would be on a processor, everybody here is on a different processor, and so on. It's been used in a couple of, at least some very interesting calculations. This is an earthquake simulation, and what you see here is a cube sphere that's been extended into 3D, and the blocks, so each block is actually a refined octree. So you can imagine, so that's how they're able to do the geometry, is by putting together several hexagonal and hexahedrons. Each hexahedron is an adapted octree or quad tree or octree. I thought this was just a great picture. So every one of these is a hex. This is a hex mesh, I guess. So these are all quadrilaterals, each of which is adaptively refined as an octree. Okay, and so here, this calculation, they had 28,000 blocks, 55 million elements. Okay, and this is part of a big ice sheet modeling project that they're involved in. So our goals were perhaps a little more modest to start with, but so we want to use P-forest to manage parallel multi-block of quad or oct trees, implement the basic block structured AMR algorithm. So we're not deviating from this algorithm at all, particularly. There's a few sort of things where the octree structure makes a certain thing simpler, but basically it's the same algorithm. So, of course, the idea is we want to reuse existing patch-based solvers. We're doing subcycling in time on the finer grids. We have to ensure mass conservation at corresponding boundaries. P-forest then guides the parallel transfers. So P-forest tells us, I need to fill in ghost cells and corner cells. P-forest gives me all the blocks that I need to do that kind of information transfer. And the other thing that it really does is in this multi-block setting, you have to start worrying about orientations of faces with respect to one another. And that can make these, make sort of standard Cartesian codes messy unless you have sort of a nice organized way to deal with that. And P-forest has that all worked out. So there are similar approaches, and I say similar, none of these are the same approach, but they all have some elements. I came across this actually at this meeting here. The building cubes method, which is developed by a group in Japan, and which I think there's a person here, I'm not sure if she's here, who's, oh, there you are, okay, good, who's, that's how I heard about this, you know, and it's this idea using fixed size grids. Jablonowski and Omke Stout, I think, are doing something similar as far as having fixed size grids. Maybe it's on an octree, maybe we'll learn about that, I'm sure we will. Jaris is a flow solver that's a cell-based octree approach. You can go out on the web. This, I believe, is also an octree-based fixed grid approach, Nirvana. And of course, I listed all these block structured AMR codes because they could all be run in this sort of operation. You can chop up, you don't need to have one big coarse grid. You could have a coarse grid that's chopped up any way you want. So in a sense, they're all kind of the same, okay, algorithmically at least. Here's just a typical example. So here, what we have, so what I'm doing, the octree is storing leaves of a grid. The leaves of the octree are fixed size grids, okay? No underlying coarse grid, just sort of a big composite mesh. So for example, this is an 8x8 grid. This is also an 8x8 grid that I don't show the grid lines. This is 8x8. And in here, right around the front, are grids that have been refined even one level further. It's just that I'm not showing the lines there. So this is kind of the adaption going on. And I was a little worried that the fact that the blocks, you're kind of forcing where the refinement has to happen on this octree, and I thought maybe that might make the refinement inefficient, but it turns out to actually be perfectly fine so far. I mean, like I said, this code is brand new. We're just now getting it working. So here's the cube. Here's our sphere grid. Okay, adaptively refined. This is an example in which I've put kind of it's sort of a pinwheel, and if you'll notice, here's the equator of the grid. So I don't have the pinwheel lined up right on the corner or at the equator, but it's going to spin. This flow will spin around that point right there. This is the two-patch topology that we have. So this grid is the northern hemisphere, this grid is the southern hemisphere, and the seams glue everything together. That turns out to be actually a really easy way to do the multi-block matching. Okay, so here's the grid. And let's see if it works. Yeah. So that's what we can do so far. It's maybe not an example that gets atmospheric scientists too excited, but in fact, if you develop these codes, you're very excited when you don't see, you know, two weird things happening in this kind of example. So refinement criterion, you know, I don't try to get too much into that business. I guess a goal I have is the code should be flexible enough that if somebody has really good ideas for refinement criteria, it should be easy enough to put in. There's, of course, a variety of ways to do this. Feature-based is what I typically like to do. Whoops. Okay. There are some issues with this grid. You know, in all honesty, the convergence that we get is between 1 and 2. Depending on which error norm you use, depending how you measure the error, depending what the problem is, I can make it look like second order if I measure the error away from the seams, away from the corners, okay? The accuracy of the method depends on, okay, I'm not doing this very well. The accuracy of the method depends on the mesh smoothness. Errors are larger at mesh seams and along the diagonals, and that's simply because the velocity from here, our method depends on propagating a normal wave from here and propagating it transversely across this edge. If you have a seam down the middle, then the velocity over here really doesn't have anything to do with the velocity over here. There's a jump discontinuity in the velocity due to the metric. And your truncation, this just messes up your truncation error. I mean, there's just no way around that, and we need to think about how to fix that, okay? So this is kind of my future work slide. So back in that meeting in March, I had this, I went back to those slides, and I had this as my future work. And I always put up something for future work, but whether I get around to it or not is always, you know, sort of depends. But in this case, I can check off that you know, I've sort of now done adaptive mesh refinement on the sphere, but not implemented in AMR or Chombo Claw, but rather in Forest Claw. So then there's a bunch of things that we need to do, you know, or actually a bunch of things I need to do. We've got to consider the more general way to handle the multi-block setting, so we can do, so for example, cube sphere, input, user, a bunch of stuff, scaling, accuracy, okay? And then the big sort of motivator for this project, at least my current motivation, is this ash cloud modeling problem. And again, this code, ash3D, is an existing code that produces, that is run in operational mode. And what they'd like to do, though, is simply, they'd like to add AMR to a code. And I don't know if any of you have ever tried to simply take a code and add AMR. It's not that easy, right? So there's all kinds of issues. One in particular, but it's interesting from my point of view in that this code takes real-time wind forecast data and uses it to project. So you've got to take this input data, which they've all got set up, and then get it into your AMR code, figure out what to do with it, and hopefully improve their tracer transport. That's it.
Any questions? Yes.
One observation about the grid you are making from the two sheets. Mm-hmm. That's wonderful, actually.
Thank you.
I think that's a resultant topology. The sphere cannot be covered by a single sheet. So it makes sense to have two sheets,
Okay.
or rather more sheets. So that's very good, actually. And the difficulty, like with the stitching the sheets, is something like what is approach, how you handle is very important in that.
You're asking me how I do it?
Yeah.
I don't do anything right now. That's why I don't get second order. I just copy ghost cells and hope for the best. And it's not terrible. I mean, there's errors and there's errors, right? This isn't an error but again, I need to, that's one of the issues we need to look at, is just how bad is this?
One more quick question. Okay, let us thank our speaker.